The two types of systems we'll look at are first order and second order. That's basically the order of the derivative. So this one is a second order system because you have an s squared, you have a second derivative. If we only had one derivative, then it would be a first order. Now, a first order system never has oscillation. It just slowly moves up in sort of a curve to your desired value. An example of this is a motor, 1 over Js plus B, where J is the inertia and B is the damping. This is the general form. So for problems on the homework, I will give you the actual form, then I will give you the general form, and you have to be able to figure out what is tau by doing coefficient matching. So we'll get into how to do that, but this first order system, you can see the input, this is a constant. We want the input to be 1, and then the system eventually gets up to 1. It takes a little while, but it gets there. That's a first order system. It never rises up above that line. Or if it does rise above, it doesn't come back down. Second order system can have oscillation. So this one, ms squared plus bs plus k, so that's the mass spring damper. It has to fit this form, 2 times zeta omega ns plus omega n squared. Zeta is the damping ratio. That is a measure of kind of how much damping or like friction is in the system. If zeta is high, there's a big damper, and that means that the amplitude of the oscillation will be small because it's like there's so much friction the system can't move a whole lot. So if zeta is big, then these peaks are very small. Omega n is the natural frequency. So that is how often it bounces up and down. If you have a high omega n, it'll bounce up and down a lot in a given time period. If you have a low omega n, it will not bounce up and down very many times. If zeta is less than 1, you get the bouncing. If zeta is greater than 1, then there's no bouncing and it looks like a first order system because it'll just slowly get up to there. If zeta is negative, then the system goes crazy. Never, never, never let zeta be negative because it will shoot up and it will never come back down. Bad things happen. The way you design your controller is very frequently uses PID control. So proportional integral derivative, the proportional control acts on the error and this decreases the rise time. So you get a high proportional control, it snaps up to the blue very quickly. So that would be, if KP is higher than the distance between the start of the blue and where the red crosses it is very small. High KP gets up to the value very quickly. Low KP, low proportionality constant, means that it takes a long time to get there. So maybe that would be, if this had a very low KP, then the red line wouldn't cross till like maybe somewhere over here or something. It would just be slower like that. Integral control, this acts on the integral of the error. So it eliminates steady state error. It looks on like, not just where is the system now, because proportional is like, where is the system now? Integral control is where has the system been since the beginning of time. So it slows things down a lot because it's got to look at the whole history, but it eliminates your error at the end. Usually we don't use integral control because it makes the math a lot harder. And that's pretty standard not to use integral. The derivative control acts on the derivative of the error. So this is the like, where are you going? It decreases overshoot and settling time. So if you have a high KD, then it will pull you back to the line once you move past it. So KD is what pulls you back to the line once you go too far. So high KD, these peaks are going to be smaller because KD is directly related to the damping ratio. If you have a low KD, you get lots of shoot because it won't see that you've gone too far until you're already like way past. So KP, KI, and KD, and then that is digital control. Now you could do this using a circuit with resistor, inductor, capacitor. So you could actually make a circuit instead of using a digital controller, but if you actually put your constants into your code, then it's a lot easier to change out. With an analog circuit, then you're kind of just restricted to whatever values of resistors, capacitors, and inductors